Welcome to The Explainer. Today we're cracking open a century-old astrophysical cold case. We're going to look at how one incredibly specific type of pulsating star became the ultimate foundation for measuring the size of the entire universe. And honestly, right now, it might literally be the key to unraveling modern physics as we know it. I am absolutely thrilled to dive into this with you because the fresh data we're getting today, it is completely changing the game.
So here's the massive, provocative question I want you to keep in the back of your mind as we go through this. Is our fundamental understanding of the universe completely broken? Because right now, astrophysics is staring down a huge crisis. When we measure how fast the universe is expanding today, the numbers just do not match the predictions we get from looking at the early universe. Something is seriously off. Either our measurements are fundamentally flawed or our basic laws of physics need a total rewrite. To figure out why, we first need to look at exactly how we measure the universe in the first place.
Section 1. The first cosmic yardstick.
The whole story really kicks off with what we call our cosmic yardstick, the Cepheid variable. These are these super-luminous giant stars that actually pulsate. They physically get brighter and dimmer over a very regular period. Back in 1908, an astronomer named Henrietta Swan-Leavitt made a groundbreaking discovery while she was studying these specific stars in our neighboring dwarf galaxies, the Large and Small Magellanic Clouds.
In 1912, Leavitt and Edward Pickering published a profound realization that basically became the bedrock of modern cosmology. They realized that a star's pulsation period is directly tied to its actual emission of light. The critical insight here is that because all the stars she was looking at in those clouds were roughly the exact same distance from Earth, a longer pulsation period meant the star was intrinsically more luminous. So, if you just time how long it takes a Cepheid to blink, you know exactly how bright it truly is. You compare that to how bright it appears to be from Earth, and boom, you've got an incredibly precise way to measure immense distances in deep space.
Section 2. Upgrading our measurements. It's really incredible to see how fast this science evolved. Right after Leavitt's discovery, Edwin Hubble used her law in 1923 to measure distances to other galaxies, proving once and for all that the universe was way bigger than just the Milky Way, and that it was actually expanding. Then, jump ahead to 1968, Wisniewski and Johnson took these observations into the infrared spectrum. This was a huge deal because it drastically cut down the errors caused by space dust. And finally, in 2001, the Hubble Space Telescope Key Project team used Cepheids to measure the universe's expansion rate, what we call the Hubble constant, to an unprecedented 10% accuracy. It was a massive triumph that seemed to resolve decades of intense scientific debate.
Section 3. The Hubble tension crisis.
But here's where the plot twist drops and things get really tense. Take a close look at the growing gap on this chart. This is what we call the Hubble tension. Over time, as our instruments got better, our measurements of the Hubble constant basically split into two totally separate camps. The blue and red lines near the top, those represent our local cosmic yardsticks, like the Cepheids we just talked about, and they are telling us the universe is expanding really quickly. But then you have that black line at the bottom. That is the cosmic microwave background, the ancient echo of the Big Bang, which represents our standard cosmological model. And as you can see, there is a terrifying gap between them. They absolutely do not agree. Our local universe seems to be expanding way faster than the standard model says it should be.
Section 4. The suspect. The crowding problem.
So, why might our Cepheid data be giving us a totally different number? Well, we basically have three main suspects interfering with our measurements. First, you've got dust in the spiral arms of galaxies absorbing and scattering the light. Second, there's metallicity, meaning the actual chemical makeup of a star might change its brightness a little bit. But honestly, as we look further and further out into the deep universe to get better measurements, those first two are nothing compared to our biggest, toughest culprit. And that is crowding and confusion from background stars.
Think of crowding like trying to hear a single whisper in a packed, noisy room. Because Cepheids are relatively young stars, they haven't really had time to drift away from where they were born. They live in these super dusty, incredibly dense, star-forming disks of spiral galaxies. So when we try to measure a Cepheid in a galaxy tens of millions of light-years away, trying to separate the pure light of our one target star from the overlapping glare of thousands of neighboring stars, it becomes nearly impossible.
And this graph perfectly illustrates the crime scene. We run these artificial star tests, and the data shows that the crowding-induced bias in the Hubble Space Telescope data can reach up to 1.5 magnitudes. Now, to put that into perspective for astronomy, that translates to a factor of up to 4 in luminosity. It is massive. If all these background stars are secretly blending their light with our Cepheid, we're going to think the Cepheid is much brighter and therefore closer than it actually is.
and that completely throws off our math for the expansion rate of the entire universe.
Section 5. JWST to the rescue.
But now we have a brand new high-tech magnifying glass to crack the case. Just look at this jaw-dropping comparison. You're looking at the exact same star region in the galaxy NGC 7250, which is roughly 65 million light-years away. On the left, you've got the Hubble Space Telescope data, and it is heavily blurred. You can clearly see how crowding is such a massive issue. But on the right, that is the exact same region observed by the James Webb Space Telescope. JWST just pierces right through all that noise, resolving those individual stars with absolute clarity.
How is it pulling that off? Well, JWST has 3 times the spatial resolution of Hubble and nearly 10 times the sensitivity. By utilizing its incredible infrared capabilities and a specific filter called the F115W, JWST manages to reduce those crowding effects by more than an entire order of magnitude in flux. It is quite literally pulling the clear signal straight out of the muddy noise.
To really drive this point home, let's look at 4 specific Cepheid targets in that exact same galaxy. The top row is what JWST sees, and the bottom row is Hubble. Those red circles mark where our target Cepheid is. In the bottom row, you can see it's just this blended blob of light. But up top with JWST, you can cleanly and clearly distinguish the target star from all its messy background neighbors. This completely revolutionizes the quality of our evidence. We are no longer forced to just guess how much of that light actually belongs to the background.
And the results really speak for themselves. Here are the Leavitt laws, those period luminosity relations we talked about at the very beginning of the explainer. If you check out the graph on the bottom left, that's the Hubble data for the galaxy NGC 7250, and you can see a ton of scatter there, a variance of 0.43. Now look at the graph on the bottom right. That's the JWST data for the exact same galaxy. The scatter drops down to 0.22. That is a factor of 2 smaller. It proves that JWST is drastically fixing our measurements and confirms that crowding was a massive systematic error just hiding in plain sight this whole time. Which brings us right back to the ultimate question perfectly posed by the source material. We're currently using JWST to rigorously clean up this century-old cosmic yardstick. But when the dust finally settles and crowding is totally removed from the equation, will this crisp new data actually close the Hubble tension gap? Or is that gap going to remain, proving once and for all that our standard model of the universe is fundamentally broken and that we need a total rewrite of physics? The data is pouring in as we speak, and honestly, I cannot wait to find out. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.